Hello.
Hello.
Hey, how's it going?
Good. How about you?
Doing super awesome. Thanks so much for asking. Welcome back. How did your ACT go a couple of days ago?
Oh yeah, sorry, I totally forgot to mention about that. But it was fine. Only they delayed. It was supposed to be in the morning, and then I went in the morning, and then something went wrong, I guess. So they just told us to come back at like in a few hours. I don't know. It was like they were at the casino, and um some of the rooms had an issue. I don't know, but I went there, and then I had to take it at around 2. And then they only started putting kids in there at 2:30, and it was a painful process. But the ACT itself was all right. I know I'm gonna take it again anyways, but I'm hoping to have gotten at least a 30 composite um first try, hopefully.
They had you take the test at the casino.
Yeah, they my school rented out some rooms in the casino, and so we went there, and then in the morning, I don't know, I guess they just weren't ready for us or something. But yeah.
We're so far in debt. Maybe they're desperate enough to start betting on you guys' scores and maybe make a come up on that.
Probably, who knows? They might have done it.
No pressure, David. The fate of our government is in your hands, but no pressure. Right? If everything screws up, it's your fault, but no pressure.
No pressure, just gotta get the 35 first try.
No big deal. You got this. So I guess I want to start by asking if you have any questions about anything we've covered so far at all, any calculus topic whatsoever.
No, not particularly.
No problems from class or from a test you want to go over? No questions about anything at all?
Uh, no, last night I had some homework due, and it was I remember one problem. Oh my gosh, I did it like 4 or 5 times, and I only did it that many times because I made a simple mistake. And when I like even one time I found what the mistake was, but then I forgot to correct it further on in the problem, and it was just horrible. But I think otherwise it was fine. It was on like looking at a function and then telling about the relative minimum maximum points, things like that, and using like the first and second derivative to find them, and then sketching them and stuff.
So if you want to go over that problem, we can, but if you don't want to, don't worry. We don't have to if you don't want to.
I wouldn't say we need to, because like I said, my only issue with it was I was just making a mistake in the beginning. And when you're in that mindset where you're getting something wrong each time, so you're just prone to making mistakes, and I wasn't slowing down or giving myself a chance to actually do it right, but I eventually got it. So
Yeah, exactly. The human mind is conditioned to look at things like that and say, "Hey, I got made this mistake and that mistake and that mistake," and you might be tempted to think, "Hey, I may not know this stuff as well as I thought," when that's actually not the case most of the time. Typically, it's just you make a little arithmetic mistake and you get completely wrong. You get the complete wrong answer because of it, and you might just think that you don't know the concept very well when in fact you probably do. So it's always good
mhm.
to be on the lookout for things like that.
Yeah, it ruins your whole attitude, but you always have to make sure to keep that up.
Exactly. It's a really healthy attitude to have. Just keep going, no matter how many mistakes you made. It's good just to know the concept well enough. So that's why I really stress that it's important to know the concept and not remember the steps to take a derivative, for example. Good to know the process like the back of your hand. So that way your mind is able to tell right away that it's like an arithmetic mistake and it's not a conceptual mistake. Like you know that it's just like you slipped a minus sign here or there instead of not knowing derivatives. So that's the main point of that. So I want to maybe start teach you one of our methods for evaluating complex limits. So it uses the derivative to help solve particular limit problems. And
Actually, good. I have a question, just one
sure,
really quickly.
sure.
Do you think I could draw?
Oh yeah, definitely.
Okay,
You should have permission right now to draw.
I do. I do.
Go for it.
Uh, oh.
And you're going to be graded on your artwork, so make sure it's perfect. All right.
I got you. Where?
Don't
Okay.
disappoint me.
Okay. Um, Okay, so it's a really simple one. We have the following coordinate plane. Okay, so this is the question, and it just asks which function is the derivative of the other.
All right. So we know what derivatives are in an algebraic sense. We know how to take the derivative. We know what the process looks like. But what does a derivative look like graphically? How does the derivative affect the way a graph looks?
Um, I think I don't. I for a linear equation, I guess it just represents the slope.
Yeah, but not just for a linear. For any equation at all that represents the slope of the function, it is the rate of change. So I want to move this off to the side real quick and maybe introduce a separate example that might help us understand this a little bit better. So I'm going to draw a function of my own, or actually I'm going to draw two functions of my own. I'm going to draw just a downward facing parabola, and then I'm going to try to draw the derivative of this function. So I'm going to call this f of x. So what I'm going to do now is I'm going to draw a graph of the function f prime of x. So what is the derivative at this point right here?
I would say 0 because that's. I mean, like looking at it, it would be the horizontal. It would have a horizontal slope at that point.
Exactly. It has a slope of 0. We have a horizontal tangent line perfectly level. So we have a slope of 0. So I'm going to use red, or actually, I think I'm just going to stick with blue for this one. So I'm going to put a 0 right here for x because when x has this value, our derivative is 0. But then what about everything to the left of that? What would be the derivative of everything to the left of this line? Would that be a positive derivative
It
or would
would,
it be a negative?
it would be positive.
Exactly. It's increasing. So it should be
So it shows when the function. So a derivative shows when the function is increasing and decreasing.
exactly. And same thing goes the other way around. So our function is going to be decreasing from here. So we start at 0, we have a 0 rate of change, increases a little bit, and then it starts increasing much faster and faster. The line gets steeper. So our derivative should also reflect that. So
Hmm.
we have 0, it's going to be very, very low, and then it's going to just get more and more negative. So the blue one is the derivative of f of x. The blue one is f prime of x. That's the rate of change. So let's take a look at both of your functions you have and see if we can do some kind of a reverse engineering process to determine which is which. So we know that we have, um, out of the two functions, this blue one has a horizontal tangent line.
Hmm.
So we want to see if this has a similar situation to the one I just drew. We want to see if it has a similar situation to what we have here. So I identified that we have, or you identified it actually. You identified that we have a horizontal tangent line, the derivative is 0. So I made
Hmm.
sure we had a point right there at 0 for the derivative. Do we have something similar in the problem you drew?
Yeah, where
I
you
think
drew
so.
the black line, I would assume that that is the right there. The point that it's tangent to is going to have a slope of 0.
Exactly. So is this enough information to conclude? Is this enough information to tell which is which?
Um, I would say yes, because when we look at y of f of x, we can tell that it's increasing as we look at it from left to right, it increases, and then it has 0, and then it decreases, but then it hits the point, it hits the vertical axis, so I think that the function just sort of stops there, and you know, as we look at the red one from left to right. Hmm. Actually, no. I don't know. That doesn't make no. I don't think so. Then.
Well, we have the zero derivative, and if the red one truly is the derivative of the blue one, well, that part at least makes sense, right? Because we have the derivative is zero right here. So this is what we're trying to prove. We're trying to prove that g of x is the derivative of, g of x is the derivative of f of x. So we have the first condition proving true. So we have a zero derivative right here. We have a zero derivative right there as well. And then everything to the left of that is going to be strictly increasing. Or actually, in terms of the derivative, because the derivative is positive, because the derivative is increasing, the original function is positive. So,
Wait a minute. Why is there
sorry.
uh why on the red function? How would that be a function of zero? I mean, how would the derivative there equal zero?
Well, because if do you agree with this fact right here? Do we agree that g of x, or this is the thing we're trying to prove, right? I'm trying to prove that g of x is equal to f prime of x. So one tool I'm going to use to prove this is by taking f prime of some value equals zero. And I'm just going to call that x. I'm going to just make it a generic x value. I'm going to call it x. So if we plug in x, do we agree that the derivative is zero in the red function? Do we agree that g of zero, or, sorry, I think I'm going to use something more generic. I think I'm going to pick c. I like to use a, b, and c for particular points. So do we agree that f prime of c is zero? If we look at the blue function, what is f prime of c?
For the blue function, yeah, I would say that the f prime of c is zero.
All right, cool. And then what about g of c? Do we agree that g of c is equal to zero?
I'm gonna say no because it's not it doesn't change from increasing to decreasing or vice versa because that's when you see those points, I believe.
Well, if we're talking about the blue function, then yeah, we do really care about increasing and decreasing. But if we're talking strictly about the red function, we don't care about increasing or decreasing. We just want to find what is g of c. So if we plug in c into our g of x, what value do we get as a return? What is g of c?
It would be zero because there is no height to it. It's still on the x-axis.
Exactly, g of c.
Oh,
So
okay.
that's how
That
we.
makes sense.
So we've proven that f of c is zero. Or sorry, we've proven that f prime of c is zero. We've proven that g of c is zero. And
Yeah.
that is enough information to conclude that at least this first part holds true. This first part has accuracy to it. So then what we want to do after that is we want to analyze function behavior of our blue function to the left of our point, to the left of the auxiliary point C. So we can tell that with the blue function, our derivative is positive, and then the derivative is negative. So I want to draw one region right here, and then I want to draw another region, not there, but here. So our derivative is positive right here. And then our derivative is going to be negative here. Or actually, hang on, sorry. I meant to say that the f is the derivative of g. So f of x is positive right here. F of x is negative right here. So whenever f of x is positive, or actually, you know what? We don't have a red function right here, so maybe that's not the best interval to use. So let's talk about everything to the right of the function. So we know that the derivative of g is positive, right? Do we agree?
Yes.
Actually, I
Well,
don't.
actually, not the wait, the derivative. Oh, yeah, yeah, yeah. Wait, no. Why would the derivative be positive for g of x?
Well, g of x is going to be the derivative of f of x. So let me erase this part. We don't need that anymore. So if f of x, or actually if g of x is going to be negative, let's identify the places where g of x is positive and the places where it's negative. So, whoa, didn't mean to do that.
Wait, now I'm a little more confused. So, so at the top where you say you have g of x is equal to f prime of x, are we saying that the red function is the original function, and when you take the derivative of that function, you get um the blue function?
Now I'm saying the other way around. So f of x is the original function. The blue is the original. And when we take the derivative of the blue function, we get the red.
Wait, so why are we calling the red one f prime of x? If couldn't we just call it g of x?
We could, but in order to establish the thing that they're trying to prove, we have to have some kind of an equation that compares them, something that connects them together in order to prove what they're trying to prove, that prove what they're asking us to prove.
So the derivative of the blue one is, oh, I see it. Okay, I get it. Yeah. Okay.
The derivative of the blue one is the red one. So the significance of the green and the blue right here that I drew, the blue rectangle indicates a place where g of x is negative. So g of x is negative in this region. And then in the green region, g of x is positive. And then the point is here, I should maybe move this along a little bit. The point's not supposed to be part of that region. It's not part of any of them. So does it make sense that the derivative of our blue function is negative? Or sorry, positive. So does it make sense that our blue function has a positive rate of change right here?
Yeah. Yeah.
It definitely does. And if we look at the other one, does it make sense that the blue function has a negative rate of change in this blue region right here?
Yeah.
Exactly. So let's take it bit by bit and just verify this. I think we're just about finished with this, but let's make sure. Always a good idea to be thorough and do quality work. So we know that the blue function has a positive rate of change. So f prime of x is greater than 0. Do we agree that that part's true? Do we agree that f prime of x is greater than 0?
For in the green region?
Yes.
Yeah. Yeah.
Perfect. Do we agree that g of x is also greater than 0 in the green region?
Yes.
Perfect. Let's talk about the blue. So do we agree that f prime of x in the blue region is negative?
Yes.
Perfect. And then one more thing. Do we agree that g of x in the blue region is also negative?
Yes.
So we've definitely proven that f of x, no, the g of x is the derivative of f of x. So we just connected this information together. We connected this information together. And we know that if we pick a point C, if f prime of C is 0, then g of C is also going to be 0. So we were able to definitively prove that g of x is indeed the derivative of f of x.
Okay.
And
Yeah.
it's kind of tricky to wrap your mind around it at first. When I first took calc, I had a really hard time understanding the graphical interpretation behind one function being the derivative of the other. And it was especially tough with concavity. But the more practice you get, the more you work on it, the easier it'll get over time. So I'm going to be putting this on my YouTube channel a little bit later today, but I also invite you to write it down or maybe take a screenshot if that's what helps you learn it the most effectively.
Okay, I'll take a screenshot right now and then I'll put it in a notebook that I have.
Cool. And if you're struggling with this a little bit later, I always recommend you take the kind of approach that I did right here. I drew one function, and then it was a really good practice for me to draw the derivative of the function on the exact same axis, just so you
Hmm.
have a good intuitive understanding of the relationship between a function and its derivative.
Okay.
I recommend trying one of the trig functions, maybe sine or tangent. It's a good thing to practice if you're trying to sketch the graph of the derivative of a function.
Can you take the derivative of the sine, cosine, and tangent functions?
Yeah, definitely. Have you guys gotten into that part in your class yet?
No, but I if that is a thing, then I should probably go and review those. I haven't done a trig in a while.
It's all right. We can definitely review those. So let me know when it's good to erase this.
It's good.
All right. So originally, I wanted to talk about something called L'Hopital's rule. It's a rule that helps us take the limit of a function using derivatives to help us make the work a little bit easier. But before we even do that, I feel like we should maybe cover the derivatives of the trig functions. So some of these are just ones you just have to remember. You just have to commit to memory. So we have The derivative of sine is going to be cosine. So we have the derivative of our function with respect to x is going to be equal to cosine of x.
Oh, is that the relationship in between them?
Yep, the derivative of sine is cosine.
Oh, wow. That's cool.
Yeah, I
I
know
didn't know
most people
that.
don't think it's interesting, but I think it's super interesting.
Yeah, I never learned that or even heard about. I mean, actually, I think my mom might have told me a long time ago, but
Your mom knows calculus?
yeah, we all used to do math, or her and I used to do math, and she used to tell me she used to use sine, cosine, and stuff when I was really young to help me solve problems, and I never really knew any of that stuff, but
I really
um,
wish I had a family who was into math like I am. I kind of feel like I'm adopted. I have 4 siblings. I'm the only one who likes math. All my other siblings hate it with a passion. And plus, I'm the oldest boy in my family, but I'm also the shortest. My quote unquote little brothers are much taller than me. So it makes me feel subconscious and short. And I think I'm adopted. And they just don't want to tell me.
no, you just got the smart genes of the family.
I don't think it's even that. I think it's just I have really weird interests because when a person is interested in things, they just spend a lot of time with it. Like I'm just kind of that way about math. Some people are interested in video games or other stuff. I just prefer to study math in my spare time because I'm kind of a geek about that kind of thing and programming too.
Yeah, I
So I
mean,
wish
yeah, but interests are subjective, so you
exactly
know
couldn't
can't
have said it better.
there's no perfect interest, or like even though some things may be popular, but really you get interested in anything.
Yeah, for me it's mostly math and piano. Those two things are my main interests.
And what was the second one?
Piano.
Piano?
Yep, I've been playing piano a long time.
Oh,
I give piano lessons too.
wow, that's crazy.
It's
I
fun.
think I tried one time to play piano, and I wasn't really good at it, but that's interesting. That can get really hard, like with both hands as well. So that's really
Exactly.
nice.
Yeah, it's a lot of fun, and it helps the brain. It helps the brain learn and grow
Yes.
faster than it would otherwise. These
Yes.
certain parts of the brain light up when you learn how to play an instrument. You're able to make neurological connections that you're not able to make with other activities. So
Yeah, because it's a cognitive not a test, but it's training, cognitive training, especially piano. That could be really hard.
exactly. So I wish I had an environment where like I wish my parents liked math as much as I did, where we would just spend an afternoon doing math together. That sounds like a really awesome life, really awesome childhood. Here, I don't know what I'm doing here. As you can see, Zoom is not my strong suit. I have trouble doing the simplest thing. So the derivative of cosine is going to be negative sine.
Hmm. Okay.
And then now we want to take the derivative of tangent. What do you think the derivative of tangent might be? And for the sake of my own OCD, I think I'm going to just type everything because I'm sorry about this, but my OCD kind of trips up sometimes where I have some things written and I have other things typed, and it doesn't look okay to me. It just doesn't seem right. So this is just due to me being crazy more than anything else. I have to type it and not write it. So what do you think the derivative of the tangent function might be?
Hmm. Oh, I maybe cosine over sine.
Well, that would be the not quite. So you're on the
Hmm.
right track. In order
That's
to find the derivative,
cotangent.
we're going to have to write it in terms of that identity, the quotient identity. How do we take the derivative of a fraction?
Ooh. Oh, you move the denominator to the numerator and give it a negative exponent. Then you use the exponent rule, I think, and then you take the derivative of the function without the whole exponent, I think.
For this one, we actually want to use the quotient rule. Do you remember how the quotient rule works for derivatives?
No, I forgot.
No problem. So let's just have a quick refresher on that. It's always a good idea. So whenever we have a function like this, let's say we have f of x divided by g of x. Nope, I'm going to generalize it. I'm going to make it u and v. So let's say we have f of x. What's going on with my mouse today? It's acting weird. So u is a generic function. V is also a generic function. F of x is equal to the top generic function divided by the bottom generic function. So to take the derivative, the quotient rule tells us we're going to do the derivative of the top, which is u prime, times the bottom minus the top, which is u, times the derivative of the bottom, which is v prime, all over the bottom squared. That is the quotient rule for derivatives. So we're going to do something similar with this one. So we can tell that in the same sense how f of x is going to be u over v, our function in this case is going to be sine over cosine. So sine, we're going to assign that to be u.
What
Cosine,
would u prime be in this case?
so u prime would be the derivative of sine. So what is the derivative of sine?
Cosine.
Perfect. So we're going to do u prime times v, but let's go ahead and write everything in first. So u prime is cosine.
So u is sine and v is cosine?
Yes.
Oh yeah, you wrote it. Okay, sorry, I didn't see that part.
No problem. And then v prime is going to be the derivative of cosine, that is negative sine. So we're going to start plugging everything in. So the first part of the derivative tells us we want to do u prime times v. So it is going to be
Cosine.
u prime
squared
times v. So it's going to be, yeah, cosine squared. And then the other part of the derivative tells us we're going to do minus u times v prime.
sine squared. This sounds familiar. This is going to end up being cosine squared plus sine squared over
You have u prime,
squared.
u times v prime. So this is going to be minus u times v prime, so minus sine of x times v prime, which is going to be negative sine of x, all over v squared. So if v is cosine of x, v squared is going to be cosine squared of x. So now we want to simplify things. So you're right, we're going to have a sine squared of x upstairs, but I want to distribute the negative. We're going to make this a plus and a plus. So I'm going to turn all of this into just sine squared of x. So upstairs we have sine squared plus cosine squared of x. Downstairs we have cosine squared of x. So we want to take it a bit further. We want to simplify it more. What do we want to do from here?
We could either do cosine, we could split the fraction and then make it 1 plus tan squared x, or if we're gonna use that one identity, I forgot which one it is, but it states that cosine squared x plus sine squared x is equal to 1. We could replace the entire numerator with 1 and then make this secant squared x.
Exactly. Perfect. So we do what we use the Pythagorean identity, just like you said. We're going to have a 1 upstairs. We're still going to have a cosine squared of x downstairs. So we're going to get secant squared of x. So this is the derivative of tangents. So I recommend you memorize these as fast as possible. Learn from my mistake. When I first took calc, I didn't do too well on the first test because I had senioritis. I know that's not a very good excuse, but I just didn't prioritize memorizing all of these when I should have.
So why wouldn't splitting the fraction work? Or would that work and get us the same answer, but in a lot more steps?
Exactly. So cosine squared over cosine squared is 1. Sine squared over cosine squared is going to be tangent squared. And then there's another Pythagorean identity that tells us that this is equal to secant squared. So we get the same answer no matter which way we do it.
Okay. So, and then there's one more Pythagorean identity as well.
I think there's actually, is there one more or is there? No, I think you're right. There's just these two.
I know of three. There could be one more, but I know of three. And you use cosine
Cotangent
squared
and
x
cosecant.
plus sine squared x equals 1, and then you can get to the other two by like just dividing cosine squared or sine squared, and then you get the other two.
Oh yeah, you're right. Probably not going to be using those in this class.
Okay, yeah. No, I think that was more of like a pre-calc thing. I had so many questions with those last year.
So I want to make sure everything is labeled. This is the quotient rule for taking the derivative of a rational function. So let's see if we can find the derivative of cotangent. So tangent, we did sine over cosine. Cotangent, we're going to do cosine over sine. And I invite you to try this one. I want you to see if you can take the derivative of this function using the quotient rule and make sure it's fully simplified, just like the other one is.
Okay, let me get my whiteboard.
Okay. I'm going to have some coffee because I feel like I desperately need it.
All right, I've got it. I'll be doing it right now.
All right.
Would this be negative cosecant squared x?
Yes, very nice.
Okay, nice.
Do you want to try cosecant?
Yes, yes, I do. Let's
Go
do
for
it.
it.
So the derivative of cosecant, right?
Mhm.
I'm not sure if this is right, but I got negative cosine x over sine squared x.
I don't think, I mean, that might be right, but we're not quite finished. So what did you get?
Negative cosine x, or negative, and then the fraction cosine x over sine squared x.
So cosine of x is the same as cosecant of x. No, sorry, cosine of x is the same as secant of x. So actually, let's maybe write it like this. So we're going to have negative cosine of x times 1 over sine squared of x.
Oh, so I just could have kept going?
Yeah, we can. So the cosine is the same as 1 over cosecant of x. No, sorry, it's 1 over secant of x. And then, actually, you know what? I think I might want to start from scratch with this one.
Yeah, okay. I did I changed cosecant x to 1 over sine x and then went from there and then used the rule to the up top, right?
So I think I'm going to do secant of x. So y is equal to secant of x, which is the same as 1 over cosine of x. So we're going to use the quotient rule. Y prime is going to be u prime times v. That would be the derivative of the top times the bottom. So that would be 0
Uh-huh. Yeah. Okay.
minus the top times the derivative of the bottom. So top is 1, derivative of the bottom is negative sine of x all over the bottom. We get cosine squared of x. So we got the same. Oh, actually, I got positive. So we're gonna make it a positive sine of x over cosine of x.
Mm-hmm.
And then I'm going to take this sine of x over cosine of x. I'm going to write it like this. I'm going to make it a sine of x over cosine of x. And then instead of writing it as just instead of writing it as a power of cosine of x, I'm going to write it like this. I'm going to break up both of the cosines.
Mm-hmm.
And then we note that this right here is tangent, right?
Mm-hmm.
And then this part right here is the inverse of cosine, or sorry, the reciprocal of cosine is secant. So this is our derivative, secant of x times tangent of x.
Okay. So then that would make I think that would make cosecant, or the derivative of cosecant, that would make it, I believe, negative cotangent of x times cosecant x.
Yes, exactly.
And it
Perfect.
would be right, it would be negative too, right? Okay,
You
yeah.
are correct. Yep.
Okay.
So, like I said, these aren't going to be going anywhere anytime soon. You're going to be using them in Calc 3 if you go that far, in differential equations, and many different math classes, and definitely in this class until the very end. So, it's in
Okay.
your best interest to memorize them as soon as possible. Don't be lazy like me.
Okay. Well, should be. I think I have more room.
Alrighty. So then let's deal with some more derivatives. Let's make sure we have a good handle on all of the derivatives we're expected to know by this point. So do you know what the derivative of e to the x is?
Of what? E?
E to the,
Uh, E as in Euler's number?
yes.
No, I'm not too acquainted with Euler's number either. But I know one of my friends asked me for help one time, and there's Euler's method or something like that. There's like 3 steps or something, but otherwise I'm not too sure about it.
Yeah, Euler's method is actually something we're going to be covering in
Euler.
this class. Euler's method, and then you're right, this is Euler's constant as well. And then this is a really interesting function, e to the x. Just like you said, e is Euler's number. And there's something really interesting about this function. It has a really specific property that no other function has. And that would be that the derivative of this function is itself. So the derivative of e to the x is e to the x. It's the only function that has this unique property to it.
But isn't this constant, isn't it like pi? It's just irrational or not? Yeah, irrational going on
Exactly.
forever.
It is an irrational constant. So this only holds for this base though. It only holds for a base of e. If we have 2 to the x or 3 to the x or any other power to the x, it won't be the same. It's going to
So why this constant? I mean, wouldn't that work with pi too, since that's an irrational number?
give me a quick second. I thought I had a good explanation for this, so let me think for a second. So if we have any other constant besides e, I'm going to generalize it. I'm going to make this just a to the x power. The derivative of a to the x power is going to be a to the x times natural log of a. And so let's figure out where we get the derivative of e to the x from. So I'm going to use the formula we have below to find the derivative of e to the x. So going by this formula, it tells us we're going to do the base to the x power. So our base is e. So we're going to take the base to the x power times the natural log of a. And in this case, our a value is e. Now, what is the natural log of e?
Natural. I don't know.
So
Natural
let's
log.
have a quick review on logarithms real quick. It's going to be pretty important.
Oh wait, when isn't it 1? I
Yes,
believe.
exactly.
So
So whenever
yeah,
we have
okay.
something like this, it's asking us what power do we have to raise a to get b. So in this one with the natural log, so you know how natural log of x is the same thing as a log base e of x, right? We're just changing the base and that's literally the difference. So
Yeah.
we're asking ourselves, what power do we have to raise e to get to itself? And that would be 1. E to the first
1.
power gets that. So this is going to be e to the x times 1. So that would just be e to the x. If we did something different, if we did it with pi, for example, if we wanted to take the derivative of pi to the x power, we would get pi to the x times the natural log of pi, which is not 1.
Okay.
And then do you know what the derivative of the natural log function is?
Derivative of the natural log. No.
Let's find out. And this is another one where you just want to have it committed to memory. Derivative of natural log of x is 1 over x.
Okay.
And then the
That's
derivative
simple.
of, what if it's not natural log? What if it's just log base a of x? So in this case, it would be 1 over x times natural log of a. Hang on, I think it's natural log of a. Give me a quick second. So I almost had it right. So it's not going to be 1 over x times natural log of a. It's going to be 1 over x divided by natural log of a.
Okay.
So these are more functions, derivatives you're going to want to have memorized. So to be fair, we don't use this one to the right very often. The one we use the most often would be natural log of x.
Okay.
This one is going to be used extensively in this class. I plan on using this quite a bit. So I want to give you an example to work on. Let's see if you can find the derivative of natural log of tangent of x. We're going to need the chain rule to find this derivative. So
The
I want
chain
you,
rule?
yep, we're going to need the chain rule. Do you remember how to use the chain rule for derivatives?
Um, I'm not even gonna lie. I don't know them by name. I just sort of know them by how they work.
No problem. It's a good idea to cover that as well. Chain rule is going to be used quite a bit.
Okay.
So, um,
Wait, in this case, would it just be where we consider ln to be a coefficient?
not necessarily a
Oh.
coefficient. Natural log in this case would actually be part of a composition of functions. Are you familiar with what a composition of functions is?
Yeah, it's where you like, if you want to take like, for example, the f of g of x, you put g of x everywhere in x for f of x.
Exactly. So the chain rule is something we use to find the derivative of a composition of functions. And it's a really good idea to have a good idea of how that process works. Here, let me move this aside for now. Chain rule for derivatives. So let's say we have some generic function. Let's say I want to use y. Let's say we have y is equal to u of v, and we want to find the derivative. We want to find y prime. So the derivative would be u prime of v times v prime. So we're taking the derivative out of the outer function. We're going to leave v alone. We're going to leave the inside function the way it is, and then we're going to multiply the whole entire thing by the derivative of the inner function. So I want to maybe use a bit of a simpler example to help us understand this. So
Is this just the rule for like two constants?
not
Or
constants. This is the rule to take the derivative of any composition of functions.
oh, so u and v were just assuming that there are variables in place for actual functions.
Exactly. They're just
Oh, okay.
variables. They're not
Okay, okay.
constants. They're not variables. They're just functions.
Oh, yeah, makes sense. Okay.
So we're going to take the derivative of sine of x squared by using the chain rule. So what function would be u in this case, and what function would be v?
Well, u would be sine and v would be x squared based off of the format.
Exactly.
But I thought, aren't those inseparable because you're taking like the sine of x?
Exactly. So the only thing we need to do now is identify a u and identify a v. We've done both of those. So now we're going to take u prime. So the derivative of sine is cosine.
Cosine, and then x squared would be 2x.
Yep. We're going to make this cosine of v. So v is x squared. So this part right here is going to be cosine of x squared. We're going to leave the inside alone. And then we're going to multiply the entire thing by that derivative, the derivative of the inner function. We're going to multiply the whole thing by v prime. So that would get us 2x. There, we're done. So the derivative of sine of x squared is cosine of x squared times 2x. And that's how the chain rule works.
Wait, how so u in this case is sine of x. So how did we get cosine of x squared?
So this right here, the cosine is equal to u prime. The x squared is equal to v. And then this 2x over here at the end is v prime. So I just took everything, I plugged everything in right here. So I found out that u prime is equal to cosine. So I replaced u prime with cosine, and then I left v alone. So u prime of v would be cosine
Oh,
of v.
v
So
is
that
x
would be
squared.
cosine of,
Okay,
yeah.
okay. Yeah.
And yeah, that's the chain rule. It's tricky when you're learning it for the first time, but the more you practice with it, the easier it'll get. So I want you to try to use the chain rule to take the derivative of the natural log of tangent of x. Let me know if you would like some help. Let me know when you're finished.
All right.
Don't mind me. I'm just amusing myself.
No, I'm working on this on my whiteboard.
No problem. Take your time. We have plenty.
Okay, so I think I got it. I think it's gonna be 10x secant squared x all over x.
Let's see if I get the same thing. So I'm going to write it first as natural log of cosine, sine of x over cosine of x. So let me ask you real quick, how do we know if we have to use the chain rule to find the derivative?
We'd have to make sure that we see two functions being composed. Or we'd have to find out, we have to make sure there's a composition of functions.
Exactly. And it looks like we definitely do. So I'm going to take u prime. So u prime of derivative of natural log is just 1 over x. And then we're going to have, actually it'll be u prime of v. So not 1 over x, but 1 over whatever our inner function has to be. So that would be 1 over tangent of x. And then we're going to multiply by v prime. So v is going to be our inner function. V prime is going to be the derivative of tangent. And then the derivative of tangent, actually, we didn't even really need to write this. We didn't need to rewrite it in terms of sine and cosine. And that's just because we already have the derivative of tangent available to us, already written above. That would be secant squared of x. So if you wanted to, you could put this in terms of the other trig functions, but this is just mainly to help us understand how the chain rule works, so it's not important. We don't really need to worry about that. But I do want to introduce something that kind of builds on this. So whenever you have the derivative of the logarithm of a function, I'm going to generalize it like this. So whenever we have the derivative of the natural log of a function like this, it will always be u prime over u. Any function we're taking the derivative of, the derivative of the natural log of any function is going to be u prime over u.
Wait, but what happened to 1 over x?
So that applies if we have just natural log of x, but this is just natural log of not a variable, but of another function. This is the
of another function. Okay.
This is a composition of functions. U prime over u would be the derivative. Any questions so far?
Nope. Just writing all this down.
Oh, sorry.
No, you're good. If you can go on because you said you're gonna post it to your YouTube, so I'm gonna still be able to write it down anyways. And I have that one question that I asked in the beginning to write down as well.
But yeah, that'll be in there. No worries. So let's see here. I guess maybe we could talk about intervals of increasing and decreasing function behavior.
Let's do it.
So are you familiar with the concept of local minimum and local maximum?
Yes. So I actually, I think is it the same thing as relative minimum and relative maximum?
They are, yes. So they
Okay.
all kind of
So
fall
then
under the
yes.
umbrella of extrema. So extrema includes minimum values. It includes maximum values as well. There can be relative, which is the same as local, relative min and max or local min and max. And then there's also something called an absolute minimum and an absolute maximum. So before we
I
dive
remember
into
those.
the algebraic part of this, I think we should use graphs to our advantage. We should take a graphical approach to this to help us understand the concept really well, and then we can apply it using calculus tools. So I want to just draw a function real quick. So let's say this is our function. Do we have any extreme values? Is there any minimums and any maximums we can tell? we can see on the graph?
We can tell, I think we can only tell one local or one relative, and it's going to be a maximum because the function is it's decreasing indefinitely. So, but we can find a maximum.
Exactly. So as it stands, we only have a maximum. This is a relative maximum, and it's also an absolute maximum. Sometimes they're the same thing. In this case, they are absolute and relative. But what if we were to limit the domain? What if we were to have only this domain? So in this case, we would have a minimum as well. So the absolute minimum function would either be this right here, or it would be this one. So this one right here that I'm coloring in right now over here on the right, this is the lowest of the two. So on our particular interval, this point right here would be our relative minimum and our absolute minimum as well, but only on this interval. If we don't care about the interval, you're right, we do not have a minimum.
So what I think you're saying is the lowest of the low is the absolute and is the absolute minimum, and the highest of all the high of all the no, the highest of all the maximums is the absolute maximum.
Yep, exactly.
So there can only be one absolute maximum and only one absolute minimum, but there can be however many relatives maximum and minimums.
Exactly.
Okay.
So we have maybe a minute left. So let's maybe talk just a little bit more about that, and then we'll be good to go. Yeah, let's deal with this one. So I want to identify all the maximums. So there's a maximum here, and there, and there. And then I want to identify some minimums as well. So a minimum occurs here, and there, in there.
Do the maximums have to be do they have to have a positive y?
Not necessarily. We could move everything down one. We could maybe have it be right there, for instance. And the maximums are still going to be maximums, even if they're both negative.
Oh, wait, is it because they change from increasing to decreasing?
Exactly.
Okay.
You picked up on that really quickly, much quicker than I did when I was first learning this. So a relative
Because
minimum,
of all the homeworks I've had.
a relative maximum occurs whenever we're going either from increasing to decreasing or from or yeah, it has to be increasing to decreasing. And then a relative minimum occurs when we go from decreasing to increasing.
Yeah. And it makes sense too.
That strictly holds for relative only.
Okay. Okay, yeah, because absolute, I think, don't you have to use the second derivative to determine if it's absolute?
Yeah, you could definitely. The concavity would help us understand that a bit better, but unfortunately, we are all out of time. You know, time flies when you're having fun, and I had so much fun. I know it's hard to tell, but I'm bursting at the seams with excitement.
No, it was very informative. And it's time is always, it always flies by when there's a lot of new information.
Exactly. So I know you missed class on Tuesday. I want to offer you a makeup session if you want to have another class
Yes.
this week, maybe this evening, or maybe tomorrow, or maybe this weekend, whatever time would work for you.
Whatever time really. Tomorrow at 10, I have one thing for school, which is virtual, but it starts at 10. So I think it only lasts an hour. So whenever I'm really available at most times. So whenever you want to, whenever is most convenient for you, I can do it.
So would 9 o'clock tomorrow morning work for you?
Yeah,
All right, cool. Sounds great. Well, hope you have a wonderful evening. I'll see you tomorrow at 9.
good. Thank you. I'll see you tomorrow at 9 as well.
See you tomorrow morning.
Tomorrow morning. Sorry. Yeah, tomorrow morning.
All right. See you.
All right. Have a good day. Bye bye.